Hello, this presentation will discuss recursive subdivision for degree 3 Bezier curves in particular. Recursive subdivision is a method for taking one Bezier curve and splitting it into two subcurves, say the first half of the curve and the second half of the curve, and re-expressing the two halves as their own degree 3 Bezier curves. This is handy for several things, most notably by splitting a curve shorter and shorter. You can approximate it by a set of straight line segments for rendering purposes. It's also useful for using convex hull properties to bound the position of the curve. So let's start off though with the mathematical description of recursive subdivision. So we're going to have a degree 3 Bezier curve Q. So Q is a degree 3 Bezier curve. The control points will be P0 through P3. And we're going to evaluate Q at some fixed value U0 by the de Castelgel algorithm. So let's draw the picture for this. So this is the same as the picture that we had in the previous video, and we're now using U0 instead of U, so Ri is equal to lerp Pi plus 1 U0, Si is equal to lerp Ri plus 1 U0, and then T0 is lerp S0 S1 by U0. So this is with I equals 0, 1, and 2, and this is with I equals 0, 1, and we get this picture here. So we want to look at the Bezier curve here, and we want to split it into two parts. So let's draw the Bezier curve. It's got tangencies at the beginning. It's got a tangency at the middle point with the line segment joining S0, S1, and a tangency at the end. So the curve looks something like this. So we want to split the curve into two halves. There's going to be the first half and the second half. So the first half is the part here. And I'll call that Q1. And the second half is the part here. I'll call that Q2. So the theorem is that when we define two Bezier curves, Q1 and Q2, from the control points that I'll give you in a moment, we get the two halves of Q. So for the statement theorem, let Q1 be the degree 3 Bezier curve defined from the control points P0, R0, S0, and T0. In other words, we've got four control points here, P0, R0, S0, T0, and they define some degree 3 Bezier curve, and we'll just take that to be the definition of Q1. And likewise, let Q2 be the degree 3 Bezier curve defined from the control points. T0, S1, R2, and P3. So in the picture here, we're taking T0, S1, R2, and P3. Those 4 points can be control points of some degree 3 Bezier curve, and we just define Q2 to be that curve. Now the theorem is going to say, loosely speaking, Q1 and Q2 are the first and second parts of Q. So what does it mean to be the first and second parts? I mean, we take the part of Q from U going from 0 to U0 and look at the curve it traces out, and that's going to be exactly the same as the curve Q1. And then we look at the part of Q going from U equals U0 up to U equals 1 and look at the curve that traces out, and that's going to be exactly the same as the curve Q2. To make this formal, we can say the following. Q of U is equal to Q1 of U over U0 if 0 is less than or equal to U is less than or equal to U0. And it's equal to Q2 of U minus U0 over 1 minus U0 if U0 is less than or equal to U is less than or equal to 1. So let's figure out what this means. So Q1, we're thinking of it as taking inputs ranging from 0 to 1. So let's look at values of U ranging from 0 to U0 as inputs to Q. Well, when we divide by U0, that makes them range from 0 to 1. And we're just saying that Q of U is then Q1 of U over U0. So as U ranges from 0 to U0, we're tracing out the curve Q1 for its inputs ranging from 0 to 1. And the same thing holds here as well. For Q2, we're looking at inputs U that are ranging from U0 to 1. And we take U minus U0 over 1 minus U0. And that gives us the fraction of the way that U is from U0 to 1. We take that fraction as input to Q2, and we're asserting that Q is actually equal to Q2 at that value here. Actually, writing these if statements isn't really necessary. These equalities are just true for all values of U, but this is the application that we're interested in, so that's why I wrote it this way. Or we can also rewrite this as Q1 of U equals Q of U0 times U. Just by change of variables there, we get that. And Q2 of U is equal to Q of 1 minus U0 times U plus U0. So another way of saying the same thing is that Q1 is just tracing out the values of Q. Q2 is just also tracing out the values of Q. When we look at their inputs between 0 and 1, we're getting exactly the two parts of Q as indicated on the drawing. This process of splitting a Bezier curve into two Bezier curves is known as subdivision. And a good question would be, what is subdivision good for? And why would we want to take a single Bezier curve and split it into two? Well, one common application is we want to do straight line approximations to Bezier curves. So we have some Bezier curve here, which is rather curved. We want to draw it with our graphics program, and our graphics program perhaps only supports straight line segments. So we might want to approximate this by a series of a lot of straight line segments. Well, we could just keep subdividing. Here's the whole curve. Here's the two halves. If they're still curved, we subdivide them again. If we're still curved, we subdivide them again. And when we're done, we get a lot of segments where a straight line approximation is good enough. Maybe the curve differs from a straight line by at most a single pixel position along each straight line segment. And that would be a rather good approximation. So let me draw a slightly more careful picture of this here. So I've got 4 control points, P0, P1, P2, P3. I'm going to draw the control polygon as a set of straight lines. And now let's do the recursive subdivision. And I'll do it with u equals 1/2. So I'm splitting it the 1/2 points, right? So I'm subdivide at q of 1/2. So here's our R0, R1, R2. And our S0, S1, and T0. So our subdivided curve looks like these two pieces here. Still a lot of curve in that, so we might subdivide again. So when we subdivide again, I'll just do the first half. Here's a new R0, a new R1, a new R2. We join them by straight line segments. Here's a new S0, a new S1, and a new T0. So I didn't draw that curve super well there, so let me fix that up a little bit. So the curve is sitting here. So this is still somewhat curved, so you could do it again. I'll use some blue for that. There's the new R0, R1, R2. Here's the straight line segments joining them. The new S0 and S1, straight line joining it, and the new T0. And so now, this looks like a pretty straight piece of the curve. So we could just, perhaps, if that's good enough to us tolerance-wise, we would just replace this segment of the curve by a straight line segment and use that as an approximate curve. So you'll notice we did this recursively, so that what we just illustrated here was recursive subdivision. And the idea is just to iterate subdivision until the curves are sufficiently close to straight. So one common way of measuring what does it mean to be sufficiently close to straight is you take the sum of the distances between the adjacent control points. In other words, the sum of the lengths of the edges of the control polygon. And you compare that to the distance from the start point to the end point. So in the big picture here, we would, from the first curve, from the original curve, we take the sum of the lengths from P0 to P1, from P1 to P2, and then from P2 to P3. So we compare the length of the control polygon to the length of going straight from P0 to P3. Now, obviously the length of the control polygon is much bigger than the length of the line segment directly connecting P0 to P3. So we could conclude then that the Bezier curve is not that close to straight. Certainly the control polygon is not that close to straight, and it would be a good idea to replace the Bezier curve by subdivision with 2 Bezier curves and then consider those 2 Bezier curves instead. So this is the general idea of recursive subdivision. The nifty thing here is that if you think about the width versus the length I need yet another color. So let's take this very last curve I did here. We can think of it had length from here to here because it started at P0 and ended at the final T0. And has width. The width of it is sort of like this little bit here, right? So this is width. And this is the length. And what I mean here is the width of the control polygon. And the length from the starting point to the ending point. So the nifty thing here is that the width goes to 0 quadratically in terms of the length. In other words, these curved segments quickly get close to straight because their width, as it were, measured in how sideways you have to go from the straight line joining the starting point to the ending point, is shrinking rather rapidly compared to the length. So we get, we don't have to iterate that many times. In this case, we iterated 3 times, perhaps 4 times is necessary, but that would be, those kind of small numbers of iterations is typically what you need. Iterating 3 times would mean breaking the curve into 8 straight line segments. Iterating 4 times would mean breaking into 16 straight line segments. 16 straight line segments is pretty good for many purposes, at least. Let's put it that way. So this is recursive subdivision, most commonly done with the value 1/2. The other advantage to subdivision is to exploit convex hull properties. So for this, if I have a Bezier curve with control points P0, P1, P2, and P3, if we form the convex hull of the control points, so what does the convex hull mean here? The convex hull means the smallest convex set containing the 4 points. So we would take the shape, usually it's 4-sided, but it definitely doesn't have to be, and we take their convex hull, which would be this area shaded red here. Then we know the curve Q of U lies inside the convex hull. So the set of points Q of U for 0 less than or equal to U less than or equal to 1 is a subset inside a subset of the convex hull of P0, P1, P2, and P3. So how do we know that? That's because the points Q of U for U in the interval 0, 1 are weighted averages of the 4 control points. So as a weighted average of the 4 control points, Q of U has to lie inside the convex hull of the four control points. In particular, that tells us that the curve lies someplace in here. It doesn't lie out 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 here. It stays inside that probably rectangular type shape of the convex hull. In coming back to this application here, if you think about the convex hull, with the first picture, the convex hull of P0, P1, P2, and P3 was pretty big, right? We know the curve lies inside it, but that's not a huge bound on where the curve lies. When we went to the first subdivision, already the convex hull from P0, T0, S0, and R0 has shrunk down in size considerably. And so we have a much stronger bound on knowing where the curve lies. It lies somewhere in this region here. Somewhere in this region joining P0, T0, S0, and R0. And the rest of the curve lies somewhere in the region joining T0, R2, and S1. When we subdivide again, now we're in this, the first subdivision is from here to here. So now the subdivision, the convex hull is this rather narrow, skinny piece compared there. And finally, when we subdivide again, the convex hull is actually this little small piece here. And the width of this thing, as we're talking about already, is shrinking rapidly to 0. So we very quickly get bounds on where the curve can occur. Even if we haven't computed exactly very many points on the curve, we get already bounds on where the curve can be. And this is handy for knowing things about visibility of curves, or whether two curves intersect, or curve intersects some other object, and so forth. So that's another nice property comes out of recursive subdivision. That's the end of this presentation. Thank you very much.